So, welcome everyone to lecture 5 of Statistical Methods in Infectious Disease Epidemiology. And today, or for this lecture, we will talk about vaccination. And there will be two parts where one of them I will be pre-recording and the second part which we will do during the lecture. So today, and for this lecture here, we're going to talk about vaccine efficacy and vaccine effectiveness. And the second part, we will talk about the screening method. So to continue about vaccine efficacy. So what is vaccine efficacy? Well, it's defined as a reduction in the attack rate, which can be attributed to a vaccine. So what you do is, if you know that PU is the risk of infection in unvaccinated individuals over an observational period from 0 to T, and PV is the proportion or the risk of infection in those who are vaccinated. Then you look at what's the difference between the two risks. So that's the absolute difference in risk divided by the risk of infection in those which are unvaccinated. So that can also be expressed as 1 minus PV divided by PU, or sometimes this is just abbreviated to say 1 minus RR. When I said risk of infection, it's important this is only one possible endpoint. It could also be risk of disease onset or disease. For example, if the disease has a non-negligible proportion of asymptomatic individual like influenza or COVID-19, then it's important to study the different endpoints. But it could also be an endpoint like death for disease. So it's important to always know what is the endpoint. And for example, in the Halloran book about vaccination studies, they sometimes denote this quantity here because it's risk of infection or the risk in those who are susceptible for VES. Okay. Right. So that's one very simple. Of course, the question is, how do you determine the PU and PV? How are you going to find them? And then, of course, the 1 minus RR. That's not difficult to compute. And of course, if you have confidence intervals and so on for RR, then this transformation also allows you to compute them for the vaccine efficacy. Okay. Depending on the study, so sometimes you don't have these risk of infection or proportion of those will be infected during a given time available, but you have a different study design depending, for example, a survival type context where you have person at risk for a given time. In this case, you can also compute the vaccine efficacy as 1 minus a hazard ratio, and that would be lambda VN divided by lambda U instead, which is a very similar setup. Hang on, to what we had here, right? Instead, we're just using the hazard ratio. Sorry about the scrolling. Okay, so is that any different? And the answer is no. So if the lambda U, so the hazard rate for a given for a short interval in time, so lambda UT, if that's small, and also if lambda V times T is small, then there's a very close analogy between the risk ratio and the hazard ratio, in as much as that the risk of infection, so the proportion of those who are infected and the unvaccinated for a given interval from 0 to T, that is also the cumulative distribution function evaluated in T for the unvaccinated. And if, as we have here, this is a constant hazard ratio, so of course that is debatable if that is really constant over time, but if it is so, then we have that for the resulting distribution, exponential distribution has a cumulative distribution function equal to this. And then if we do the Taylor expansion around 0, which is an okay approximation. If this quantity here is small, then we get that this is equal to lambda ut, and that PV is equal to lambda VT. And of course, if you then take the ratio between the two as we did here, then we would get this quantity here. So in this case, we can see that finding there's an analogy between using the risk ratio or the hazard ratio. Maybe it's just a bit of terminology, and the Halloran book, the book chapter 2, which I provided as reading material for this lecture, is a bit more strict about this and presents several quantities, but it's important to distinguish between vaccine efficacy, which is a measure for the effect of a vaccine typically in controlled clinical trials in the individual, and what is called vaccine effectiveness, which is the effect in population under field conditions. So there are two aspects which make vaccine efficacy different from vaccine effectiveness. First of all is that a vaccine effectiveness is evaluated under field conditions. That means there are important factors like vaccine storage, vaccine schedules, and human error, which play more into which play a bigger role compared to the clinical trial setting, where, I mean, of course, this can also happen, and these, of course, also have a certain meaning, but of course, these are still under controlled conditions, and of course, on the field condition, even the best scheme cannot maybe be adhered to because of problems transporting a vaccine at minus 80 degrees through the desert. So, of course, there are things to take into account here, but more importantly, also the vaccine effectiveness is considered in the effect in the population on the field condition. There's one important difference here is, of course, that herd immunity, or sort of the reduced spread because of people being vaccinated, because already, for example, a herd immunity threshold has been reached, is also taken into account. So, of course, this is an indirect effect of the vaccine, but it's, of course, very important effect, which should be taken into account when looking at this. So, how can we estimate vaccine efficacy and effectiveness? You can take the efficacy from a classical, for example, cohort or case control design, which you also know from other courses in epidemiology, I would reckon. And here the vaccination status of the individuals is the exposure variable. That is sort of like where the vaccine or the yes, no. So of course you could, for example, have a placebo-controlled trial where you say some of them are vaccinated, some of them are not vaccinated on purpose, because we will maybe for each flip a coin, we'll blind for the observer the study in order to evaluate, and don't have a bias from that people are known that they are vaccinated or not vaccinated. Okay, and of course, outcome is whether individuals develops the infection, which would be, or the disease. So maybe here it would be better if I would have written in infection here if we're looking for VES. Of course, there can be all kinds of additional things you want to do. So you want to use a regression context, for example, to adjust for possible confounders in such a study. Typically, age could be an important factor, because vaccine efficacy develops different in individuals at young age versus high age. So really the Bible to read on such estimation approaches is the Halloran book, where I provided 2 chapters or parts of 2 chapters as reading material for this. So let's look at specifically at the cohort design, which is the easiest way to do it. So let's say we have NV is the number of vaccinated individual, and NU is the number of unvaccinated individual in our cohort, which are subject to follow up, and we will say there's censoring is not an issue here. So, and let also similar YV and YU be the number of cases during the observational period. So again, depending on the endpoint, that would be either those who are become infected, or those who develop disease, or those who die, depending on the endpoint. you choose. And then this estimate can be obtained by looking at the proportion of those in the vaccinated group which became infectious or infected, and the proportion in the unvaccinated. And then we have our estimate for the vaccine efficacy. And since this is a relative risk, we can get confidence intervals by transforming the intervals for the relative risk, as I mentioned before. And if you want to, you can use a Poisson regression approach using person years as offset in order to get a regression context in order to adjust for these. But then we are already actually stepping into the hazard ratio approach. So here's a very famous clinical trial named the first clinical trial, large-scale clinical trial for a vaccine study, which was against polio vaccination in 1954. So at that time, incidence of polio was about 50 per 100,000 children. I'm not sure exactly about the time period or if it was per year. I would have to check that about the incidence. And what they did is Francis developed a vaccine for polio and tried this out under field conditions. So children in 1st to 3rd grade were investigated in this placebo-controlled trial, or to be honest, I'm actually not sure it was even a placebo-controlled. I would also have to check that, but I guess it was so there. So we have the two groups, those who were vaccinated, yes, and those who are not vaccinated. And then we have here if they got the disease, yes and no. So there were about 200,000, somewhere more, about 200,000 in the vaccinated group, and 200,000 also about in the non-vaccinated group. And 57 of those who were vaccinated became infected with the disease, and 142 did not. So please be always aware, just getting the disease, there are probably several severity stages, and of course, just getting the disease doesn't mean that you got into the most serious stage. So there could even be a reduction in seriousness despite that you got disease. But we shall be interested in the endpoint, sort of like got disease, yes, no, or VES also. So this was one of the largest control trials ever conducted. And of course, the question is, does the polio vaccine work under field conditions? So we can use any 2x2 table analysis. So here's one which is implemented in the EPI package, but of course there are also others. So here are the data, the 57 out of the about 200,000 and the 142 out of the about also 200,000. We would just simply set up the labeling of this, and then we can use the 2x2 function of the EPI package to compute the relative risk. So this is here, and the one they have 1 minus the relative risk. Here we have point estimate, and here we have the lower and upper bound of the 95% confidence interval, and we see that the vaccine efficacy here is about 60%. So it's not a huge number, maybe if you compare with some other numbers that you heard, but this is actually really, this shows that this is a success, because you also have to sort of, it reduces the risk to get infection. Of course, the next stage would also be to look at, does it reduce severity of the disease, and also does it, in case you still get it, does it then also reduce your ability to transmit further disease? And of course, if these are also reduced, but because then of course this is also important. Okay, and just to say, sort of like, 1954 is quite some years ago, but here's an example from really very up-to-date example. So this is the famous phase 3 placebo-controlled trial for the BioNTech mRNA COVID-19 vaccine. So there were about 42,000, 43,000 individuals in this study, and again, same setup as before. So there were 8 in the vaccinated group and 162 in the non-vaccinated group, which were infected by the disease. There are also some other endpoints in the paper. So if you really want to see stuff like this in action, then it's really worthwhile to look at this paper, because this is really came out December 2020 in the New England Journal of Medicine, and meant that yes, we within a year or less than a year have been able to find a vaccine against this new disease, which we did not know so much about even when it started. So that is actually a really impressive scientific achievement, and with an effectiveness which is really sort of like, yeah, let's put it a bit positive, beyond dreams. This is really sort of like really, really impressive high vaccine efficacy. Okay, but it's not just necessary to do cohort design. You can also do it the other way around. You can use case control study design. So you look at the number of cases and the number of controls, and P cases and P controls denotes the respective proportion in those groups who were vaccinated. And then you compare the two odds. So odds for vaccination in the cases group and odds for vaccination in the control groups. And then you get here an odds ratio for this. And of course, if the attack rate altogether is low, which we hopefully hope is true for an infectious diseases, we know that the relative risk and odds ratio are approximately the same. And then we can use our standard definition of the vaccine efficacy to get an case control based estimate of vaccine efficacy. And here we can again use a logistic regression to maybe allow for adjustment of covariates by modeling the individual odds, by modeling the dependence of the odds ratio in terms of confounding variables which you would like to adjust for. Okay. So there were sort of like two approaches looking at vaccine efficacy. I would like to sort of go a bit further and also talk about vaccine effectiveness. More details in the chapter 5 of the book. So one, this is something which we call sort of this type 3 estimate, which looked at the overall effectiveness. So also studying the indirect effects of vaccination. Is one sort of like important component of when you start to look at vaccine effectiveness instead of just efficacy. So for this, let RFT be the reproductive number at time t when the fraction f is of the population is vaccinated. And so such a measure, which is really talking about vaccine effectiveness, is by comparing the relative reduction in the reproduction number. So looking at RF of t compared to the original R naught. So that's a different way even to express the vaccine efficacy. But now you also take these population-based effects into account, because R naught, as you know, is sort of these 3 components which you multiply, sort of like contact parameters, how many contacts do we have within a given interval. Then there's a probability parameter. What is the probability that one of these contacts, if it is with an infection, that it will actually be a transmission event, so that is the disease will be transmitted to you, times the average length of how long people are actually being infectious. So there are these 3 components here in R naught, and and then it can be computed like this here, because the RF of t will be that the number of susceptible reduces, or the proportion of susceptible will reduce by a certain quantity, right? So so one simple way is, of course, and I think we will have that on the next slide. Yes. So one simple quantity is to say, well, the proportion of susceptible. Maybe I should write that here. And okay, no mouse to see. I would say R naught, as I mentioned, is sort of like contact times probability of a transmission times duration of this. And there's a last parameter. If we don't talk about R effective, it's sort of like C times P times D times the proportion which is still susceptible, right? So that's S of T compared to S of naught, I would say, and then it's RE of T. And if we vaccinate, of course, this one here will also not simply reduce because of individuals being turning from susceptible to infectious, but because people are less, there are less susceptibles available. So this one here would, for example, be 1 minus F instead. So we would have that RE of T if there's nothing else going on, or that would be probably RF of T would simply be if R naught times 1 minus F in the simplest setting, right? Okay. Right. So let's look at this scenario. If you have a vaccination which is perfect, so it induces complete protection, so VES is equal to 1. And what's the minimum proportion we need to vaccinate in order to eradicate a disease? So we can use our homogeneous modeling for this. So if you have a homogeneous model, we, as you showed, we have RF is equal to R naught times 1 minus F. Then we can simply push around the equation until we have that F star is bigger. I think I should have a bigger here than 1 minus 1 over R naught. So if R naught is 3, which you could say is maybe a realistic number for COVID-19 settings, means that you need to vaccinate 67% of the population in order to achieve the what sometimes is just referred to as herd immunity. But what it means is that at this point your R naught or effective R naught becomes smaller than 1, and from then on it starts to decline. It doesn't stop on that day. You reach 67%, of course, but that's when you have the decline from that, because the effective reproduction number became smaller than 1. So if you, instead of a fully sort of working or perfect vaccine, you can use also sometimes you will meet another concept, which is called a leaky vaccine. That means everyone can become infected still, but the probability of a contact being infectious, so if you meet somebody, it's not, the probability is not P anymore, but it's now theta times P, where theta is between 0 and 1. That means that the vaccine efficacy, and I think this should have been S instead. Then this is given by 1 minus theta, and in this case we then have, or put in the other way, that if the probability of becoming infected, or the transmission probability, if previously it was C and now it is instead C times theta, then of course R1 is just theta times R naught. And if you do that and you say a proportion of F is vaccinated, then your RF is equal to F times R1, which are those with a reduced probability for transmission, and then it's 1 minus F of the old ones, so that's times R naught. And if you don't worry about what happens, let's put it in another way. If the Vs, which would here be Vs, if that is high, then of course the proportion of those who are not being lucky enough to benefit from the vaccine could still have an effect in that they are not as much transmitting the disease. So that's sort of like what's the VI, you could say. But if, of course, VES is already high, then, of course, the proportion of those still being able to transmit, and maybe at a reduced rate, and that part is sort of negligible at first. So if you say VS is high, it doesn't matter. We can simply ignore those in terms of onwards transmission if there's anything going on. So we don't need to make a choice for them. And again, if you want then RF to be below 1, that means this F star is has to be above this fraction, this product of two fractions, where we can recognize the part we had just from before. So if we say the vaccine is leaky, in as much as that it reduces the rate of possible transmission at given that there's a contact by factor 10, then we, instead of the 67% we had, we need to vaccinate 74% because it's now a leaky vaccine, right? So if that would have been 0, then we would have, as you see, we would just here have the 1, and then we would have the expression that we have previously. So you need to do more here, of course. And of course, depending on how this one here looks, you have to do quite some more. Okay, maybe just sort of like as a final outlook for an all or nothing vaccine, which is sort of like the same view to look at, but just a different interpretation, namely that there's a certain proportion of those vaccinated, they are completely protected, and a certain, and that's proportion is alpha, and the reverse or the opposite, so 1 minus alpha is the proportion not protected at all by the vaccine. And in this case, then the critical vaccination fraction is given by this expression, where you just see that we, instead of 1 divided by 1 minus theta, we now use 1 divided by alpha. So again, for R naught, we get, so again, sorry about the number here. This is supposed to be the 74% we had before. So this needs to be corrected. Again, in both cases, the leaky as well as the all or nothing critical fraction of this type, that you have VES, 1 divided by VES times the fraction here, the 1 minus 1 over R naught. And this 1 minus 1 over R naught is also some in the very early stages of the COVID-19 epidemic was also sort of propagated as this is the level you have to reach in order to achieve herd immunity. And herd immunity was at this point because there were no vaccination inside. It was sort of like, this is what you need in order to have a reduction because of herd immunity. And then, of course, this percentage here is sort of like something this 70% with the infection fatality rates that COVID-19 has. Then you can do the pretty simple math and get to that. You get quite some substantial numbers, which made many public health people react early on to say this is sort of very serious. Things need to be done. Maybe just as a final outlook, so far when we transferred into the domain of dynamic modeling again, sort of like SRR models, But you can even sort of like look at this, how sort of these were more static. But if you, for example, as for COVID-19, but in also other cases have, for example, distribution problems, sort of logistic problems, sort of like to roll out vaccination, then of course timing is also very important. So the time dimension needs to be taken into account. And then you can start off, instead of having these sort of models that I showed here sort of at the end, instead you would look at how is the dynamic, the temporal behavior of all of this. And then you sort of start to use the SIR model, for example, again, a deterministic SIR model, and simply add vaccination states here. So here's an example from a science paper, also about COVID-19, where they have even age stratification, but that's not here in the figure. But basically at heart, it's an SEIR model, which you then sort of like split even further into two, those who are vaccinated and those who don't benefit from vaccination. So here, this is an all or nothing model. So this is the vaccine efficacy they have here. So a proportion VE sort of migrates from S into V, and a proportion 1 minus VE moves into this category here. And then they have additional effects also, if, and you don't want to know all of this, about those who are, if you do some zero testing before you decide of whether you will have a vaccination or not, then it depends on the sensitivity and specificity of these tests, but in principle, you can ignore that. And then you have that if specificity is 1, then they will all go in here, and if because there will be no test to decide whether they will go there and there. But this is the stuff you will then use in order to plan what's the best vaccination strategy for. So for this, maybe if you want to see sort of SAR modeling in action, sort of a bit data free, of course, as always, but sort of like trying to look ahead, given reasonable assumption about the parameters. What is the best way to vaccinate the population? Should you vaccinate the active individuals, those who have many contacts, but because they are typically younger, have less sort of impact, are less impacted by the disease, or should you, the other way around, vaccinate those who are really at risk of becoming very serious ill from the disease, but maybe they have less contact. So again, this depends very much on the assumptions you make. But for example, this paper here, and maybe that's worth a read if you want to, or maybe that's part of something you would like to look at in your project. You can start to see that vaccinating the elderly population first, because they have the highest infection fatality rates, is the best thing you could do under these assumptions for COVID-19. So this is why many countries follow this vaccination strategy. And this is sort of like one paper which confirms this, but as an example, in Germany, this is the stuff you would also do to model at a public health institute, for example, would be a typical task you would do through such a pandemic. Okay, so that was sort of like a vaccine efficacy measures, even vaccine effectiveness measures using sort of traditional case cohort, case control, case or cohort designs. But there's also other ways to do that. And I will talk about this in the lecture on Wednesday. But for now, I'm going to stop the recording here, and I will see you in the lecture on Wednesday. So bye-bye.